Thank you very much. It's a great pleasure to be here today to talk through some of the work that we've been carrying out over a number of years. And I'd like to thank the Royal Society of Victoria for this opportunity to talk about bioremediation, restoring contaminated ecosystems, and doing that in a natural way so that we restore effectively back to something like that ecosystem used to be, and being a functional system. So today, I'm going to talk about various aspects and to go through the presentation to introduce the concept of contamination. And it's not just for this continent, it's a global problem we're all facing in society. What do we do with the contaminants? How do we treat these environmental contaminants? And where does bioremediation fit in? What is bioremediation? We'll have a look and examine the different technologies involved in that. Then, really to illustrate how effective bioremediation can be, we're going to look at bioremediation in action against some of the common contaminants all over the planet. They are petrogenic hydrocarbons, crude oil and their products, which are shipped and pumped around the world and obviously end up, unfortunately, through accidents or some spills in the environment. And then we're going to have a look at more difficult contaminants, chlorinated hydrocarbons, and they're in the groundwater. And how does bioremediation work in that aspect? And what are the future challenges? What's going to happen in the future? What is tomorrow's bioremediation? As we'll see, a lot of these bioremediation actions are historic, dealing with contaminants from the past. But we're going to face some challenges in the future with new emerging contaminants. So that's the approach we're going to look at. First of all, global contamination. Unfortunately, it's everywhere. Contaminants are found from the stratosphere through to the deep oceans, North Pole, South Pole, it doesn't matter. It's present in wildlife. It's present in all of us. We all carry legacy of contaminants. And unfortunately, that includes newborn. So this is a serious issue. There are over 3 million sites contaminated around the world, and they're only the ones we know of. It's likely to be 3 times that number. So if anybody thinks they don't live very far away from a contaminated site, it's unlikely. These contaminated sites are mainly in urban areas, so associated with anthropogenic and human activity. And unfortunately, at this moment in time, most of these contaminants are left untreated. And just to illustrate the issue and the health implications of contamination, in 2015, it was considered that 9 million people in the globe died prematurely. That's 3 times more than deaths through tuberculosis, malaria, and AIDS, all because of pollution. It's a serious environmental and a health issue. And just looking at some of these visions here of oil, either in the oceans or on the beaches, it's a real problem. It's been recognized. A lot of people have highlighted the issue of global contamination, and I highlight this article from Rockstrom et al. It was published some 10 years ago, which was all about the safe operating space for humanity. And the planet is in green in the center here. And these are the 10 boundaries that Rockstrom et al. Examined. And the red is how far we've exceeded the boundary, the safe boundary. So, for example, climate change, we've exceeded that. Nitrogen, the amount of nitrogen free in the environment, we've exceeded that. It's danger. Biodiversity loss is a really alarm bell. And here's the interesting thing. Chemical pollution is this slice here, not yet quantified. So whereas we've got very good ideas of all these other potential environmental impacts, we don't know about the environment. We're not quantified. We haven't done enough research to assess what's out there and what the potential damage is. I think that highlights what we need to do in future research. Now, looking at contaminants, we see some really classic examples in the past and current of contaminants. The Exxon Valdez oil spill in 1989 off the coast of Alaska was a turning point. It's a turning point in our understanding of environment and sustainability. Up to then, pretty much contaminants were entering the atmosphere, the environments regularly, but in smaller quantities with the perception that the environment could deal with these contaminants, that the environment was some sort of a sink that would be able to cope with all of these contaminants. This oil spill, which went 470 miles on this beautiful, pristine coast of Alaska, really identified what the issue is. The potential of, in this case, an oil spill from the Exxon Valdez here, damaging this pristine environment. It was a wake-up call for everybody, and it was the start of really mainstream bioremediation, work by Ron Atlas, who did a lot of work on restoring those environments using natural processes. And the biggest oil spill of all happened, of course, in 2010. For 87 days, the Deepwater Horizon oil rig leaked 3.19 million barrels of oil into the Gulf of Mexico. A true environmental disaster. But besides all of these very large, very public contaminations, there's contamination occurring all the time. Small amounts on agricultural farms, through diesel spills, through people changing their oil in the car and just flushing that away, for using pesticides and herbicides improperly. This environment is constantly bombarded by a whole array of contaminants. And these contaminants are becoming more and more complex. They're going to cause more and more issues because more and more they're man-made chemicals. They're not naturally occurring. And we'll come back to that as we go through. We can find, for example, perfluorinated compounds in areas that are uninhabited. So that they're into the stratosphere, they're being deposited all around the world. They're in the Arctic, they're in the Antarctic, they're in whale populations, they're in polar bears. So, unfortunately, obviously where there's a lot of urban environments, then you tend to get an accumulation of contaminants. And where there's dense housing, you would start to see much larger concentrations where it's, treatment systems are not appropriate or have been outdated and just can't deal with the numbers. But unfortunately, once those compounds are in the environment, they can be transported vast distances. So truly is a global issue. So contaminants are around. There are many ways of dealing with these contaminants. In the environment, we can incinerate them, especially if they're oil-based products, crude oil. Incineration is certainly a way of destroying it. But you can see from this image that there are potential contaminants coming out of those chimney stacks, dioxins. And as we're all aware, nobody wants to live by an incinerator. Everyone's aware that this is an environmental risk. It creates an ash, which still has to be disposed of. So incineration is one way forward. But in Australia, very few incinerators are being operated. In the US, there's many more. Perhaps here we take on the idea of using landfills, burying our waste. And that can include household domestic waste, toxic waste, asbestos, all sorts of things which are buried in these very large landfills. It's a cheap way of dealing with an issue, but it doesn't solve the problem. It's essentially a legacy. We're just leaving it for another generation further down. So it doesn't destroy the contaminants, it just takes them out of sight. So that's not really a sustainable answer. Solidification is actually using some sort of a binding matrix like cement. So you take contaminated soil, you bind it with cement so it becomes a solid, so it doesn't leach, and you either bury it in a landfill or you place it under a bridge in the cement. Again, you're not having any cleaning up of those contaminants. It's just putting them away. And of course, as we all know with cement, concrete, eventually it will leach and it will start to break down, and those pollutants will once again re-emerge into the environment. Thermal desorption, heating the soil at very high temperatures to volatilize the contaminants. Very effective technology, very expensive, but it does remove the contaminants and they can be used as an energy source if it's an oil-based product. Problem is that soil is dead. There's nothing you can do with that soil. Soil is a wonderful matrix. You can plant crops in it. You can put buildings in it. A very large story. And that's based around the functioning of a soil, not just the chemistry, but the biology. If you destroy it, you destroy the structure, it's a dead resource. Bioremediation, this is the subject of today, is using naturally occurring organisms present in the environment, present in the soil, present in the water, to effectively attenuate the contaminants once and for all, destroying the contaminants. So producing carbon dioxide and water. So we solve the problem now. We actually leave that soil functional. We can reuse that soil. It's a valuable resource. So this is what I'm going to base today on. There's a lot of research has gone on to using these naturally occurring systems. And we'll learn more as we go through. So what is bioremediation? This is using biological systems, especially bacteria, although plants have been used, of fungi, but mainly it's based around bacteria to remove those harmful contaminants, oil, pesticides, all sorts of compounds from the environment. And it's really interesting because, of course, microbes are very, very small. You can't see them without a microscope. Here's to illustrate that, an image of a pinhead. And look at the size of the microorganisms on that pinhead. This is E. coli, common member of the intestine. How do these organisms, so small, potentially have such a profound effect and sustain our environment? Why are they so important to environment, human health, and to life on Earth? Well, let's just explore that for 1 minute. It's all to do with the number. Very hard to count the number of bacteria in the world. It's an estimate, of course, but the number is estimated to be 5 million trillion bacteria. That's what it looks like in new numbers. So many of these organisms, so small, but so many. Let's put this into context. Humans, well, we've one species. There's 7 billion of us. And if you take all the dry biomass from all of the human population, it's 105 million tons. Think of another very common member of our planet, the ant, humble ant. But there are 12,600 plus species. They're somewhere between 10 to the 7 and 10 to the 8 billion ants. And if you took all of the dry biomass of these ants, you've got 300 to 3,000 million tons of biomass. So although they're much smaller than a human, they're so numerous that the biomass of ants is much greater than the dry biomass of humans. Now come to bacteria. There are between 10 million and 1 billion species of bacteria. They've been around for billions of years. They've evolved effective ways of surviving, of using every natural substrate on the planet. There are 300 to 500,000 million tons of biomass. They're by far the biggest biomass on the planet. And that reason makes them very, very important to all living organisms on the planet. So they're the fundamentals. They're the engine room of the bioremediation. What can they do? Well, if we look back of the history of bioremediation, a third of all bioremediation activities at a commercial scale have been through petroleum-based products, oil spills, diesel spills, tanker spills, always a very large amount of petrol and crude oil products being transported. And microbes have lived side by side with crude oil for billions of years. They are very effective organisms at breaking down oil and using the carbon as a means of growth. So that is the fundamental of bioremediation. Then there's the historical. We're all, as urban sprawl occurs, as more people are living in urban areas, the areas of cities that were once industry are now suburban. And so a lot of activities that used to happen, like dipping of wooden fence posts to prevent them being rotting in the field, all used to be on the outskirts of town, which are, of course, now very much in suburbia. And they need remediating. Things like creosote, a derivative of oil, is very carcinogenic, very toxic, but was very effective in dipping wood to prevent contamination. Sheep drip, places where pesticides are applied to animals and crops, where they're manufactured. Solvent industries, pesticides, anywhere where industry has been around for some time will create contamination because perhaps 50 or 100 years ago, the idea was that the environment was a good receptacle for all waste. So there was not an effective way of treating these wastes. So they built up as a legacy item. Why bioremediation compared to all of those other technologies? Well, low cost. You don't need to have a lot of infrastructure. Microbes work for free. They work 24 hours a day, 7 days a week, 52 weeks a year. They're non-stop, and all you need to do is to look after them. Make sure they've got what they need to grow. Public acceptance. When I first started bioremediation on a large scale, commercially, through a company, we were once accused of not carrying out a bioremediation on a site because we didn't have big diggers, we didn't have transporters, we didn't have dust. It was just a few scientists following the microbial community. And of course, that led me to realize that we need public education, understanding of what bioremediation was. So we make sure now that we do that to explain to neighbors what is exactly happening. And microbes are phenomenal at converting toxic pollutants into harmless products like water, like carbon dioxide. It means there's no waste, no requirement for disposal. That site can be cleaned and restored to its natural functions again. I'm not saying that you can return something to how exactly it was, but it can return to something which is safe, return that has an ecosystem, an effective ecosystem, delivering ecosystem functions, which is very different to incineration or thermal treatment. And there's no wonder then that there's a real potential to develop commercial technologies based around these microbes as a sustainable approach, a sustainable technology for the future, for dealing with our legacy wastes and our future wastes. But there's a word of warning, and that is that bioremediation sounds fantastic, and it is fantastic, and it works very effectively, but it has to deliver exactly as any of those other technologies. So it has to be effective in a short period of time, it has to be manageable, and above all, it has to be the same cost or even cheaper. Unfortunately, that's many of the times that bioremediation is used. It is the cheapest option, not always the quickest. Digging and dumping into a landfill to build a housing estate is much faster than 6 or 12 months of trying to get bioremediation occurring. But so on those issues, it's impossible. It has to be that kind of a time frame. Nonetheless, there are many opportunities for bioremediation. And it's not just one technology. And in fact, no site is ever the same. Every site starts with the site investigation, sampling, looking at the topography, the groundwater, and starting to develop a remediation action plan based around the site. Sometimes that is doing nothing because every environment, every ecosystem has resilience built in it and therefore can deal with contamination to a certain extent. So if you just leave the environment, it can naturally attenuate. And all you do is use the natural microorganisms present in the environment and you monitor it and you follow the degradation of the contaminant. And this can take years. So it's used and it's the most cost-effective treatment when you're not going to reuse that ecosystem for anything else. If you just want to return it to its natural format, that's the way to go. But if you need to stimulate the organisms that are present in the environment, perhaps they are the environment is too degraded. The levels of contamination are too high. We then have to intervene and help those organisms to restore that environment. And that might be adding nutrients like nitrogen and phosphorus, or even sometimes oxygen, just air, into the system, as one of my former students, Taylor, is doing here, injecting nutrients into the groundwater so that it will stimulate the organisms to break down the contaminant. Sometimes we can use plants, phytoremediation, very good at uptaking heavy metals from metal-contaminated soils. They can bind them into the roots, into plant material, and then you can remove the plants and even, if it's a precious metal, recycle those metals that are present in the plants. So It's a great example when we can use plants to assist the natural organisms in the bacteria in the soil to achieve an outcome. We can use old products. So this is moldy straw, a waste product in our agricultural system. We're not using anywhere near as much straw as we used to, but they're full of organisms, which when you add them and bury them in the soil, stimulate the degradation, the breakdown. There's a lot of fungi in there, which are really effective at breaking down some of these compounds. So using plant dead biomass, necrophytoremediation. And then finally, there's the adding an organism. So you might have no naturally occurring microorganism that can break down a contaminant. And therefore, you have to find one. There are many commercially available, and we'll see some of those later. But it's fraught with difficulty. It's called bioaugmentation, when you augment the natural community with a non-native organism, and it has to then survive. Far better to use the naturally occurring organisms which are present in the environment. So they're the different technologies. And each of those technologies have slight nuances which you develop as you address the single contaminant or the multi-contaminants at every single site. This is probably my favorite slide, and this is where I pay tribute to all the students who've come along and worked with me over a number of years. I've been fortunate to have more than 80 PhD students work with me. And here's Narelle, a PhD student, just starting. And you can almost see the weight on the shoulders of a project, which is going to remediate the material inside this. It's called tank bottoms. It's very difficult to clean tanks out in between storing oil. You know, oil is not homogeneous, and large solid components solidify at the bottom, and every so often they have to be cleaned out. And Narelle has just been given her first sample. You have to crawl in through a manhole to get the samples. And here's her first experiment, where she's got some of this very difficult oil, and she's going to work out a solution. Absolutely move forward to an end of a PhD. We go through the idea that she's growing organisms in the environment, in a laboratory, in a small shake flask. We've all done it. A little bit of nutrients in there, a little bit of the contaminant oil, shaking it and just following what grows. Skip 4 years now. This is Narelle's final experiment. This is 1,000 cubic meters of diesel contaminated soil. And we were very fortunate to have a pad where we could carry out such analysis. So remember that, back to the lab where you have that media in a flask. Well, the media is being sprayed onto the soil, not from a flask, but from a tanker. Shaking, helping those organisms to grow. Well, now we have a front-end loader. That's what's doing the shaking. So from those humble beginnings, developing a solution which is now effective in the environment. Here's the oxygen going, the air being pumped through. You can see the nutrients being added along with the microorganism. And what do we get? This is total petroleum hydrocarbons in this particular soil. Started off very high, 40,000 milligrams of oil for every kilo of soil. And over 6 months, 5 months in fact, you can see the level going down. And that dotted line tells you at what level your contaminant has reached so that it is fit and safe for reuse. So that soil, very high contaminants using bioremediation, was treated down to very low concentrations, which could be used in a garden. So low concentrations, all through many of these student applications. So, no lab coat. Lab coat was in the middle time. Now it's PPE. Everything is protective. It's just a capture in 1 or 2 slides, the essence of bioremediation development. I think generally that when oils are in soils, they don't transport readily because they tend to bind to organic materials. So if it's a clay material, if it's got a lot of organic matter, then those bitumens, those oils will be tightly bound to the soil matrix. And you may get wash out of some products, of breakdown products, or some other parts of the oil, but generally not that very heavy molecular weight compounds. But nevertheless, once they're in the soil, they're very hard to break down. And they do have an impact on that soil community and can really, affect productivity of those soils, not just in terms of agricultural productivity, but the way that they sequester carbon, the way that they provide nutrients to plants by recycling, all of those things. So it has a very deleterious impact on the soils, and potentially can travel through to the groundwater if it's sufficiently mobile and lightweight compounds. Okay, so now we come to some examples to really see bioremediation in action. And I said before, this is a global issue. And you'll see the first two examples actually come from Singapore. And not the island of Singapore, but the island of Jurong, just on the outskirts, just off Singapore Island. This is what Jurong looks like. It is the heartbeat of Asia's oil production. Produces almost all the petroleum products that comes to Australia. In Australia, most of our oil refineries have closed down, including the one here in Melbourne. And now we're taking our products from places like Jurong Island. And obviously they have a lot of oil spills, and not just in the soil, but also in the water, the water in the ground. And we went to them with a PhD project to Jurong Island curators and said we would like to try bioremediation. They liked that because this is a very dangerous area. You cannot get incinerators, you cannot get thermal treatment. You don't even want diggers flying around there. They want a very non-invasive approach to cleaning up. So the big advantage for bioremediation. And this company were world leaders for us at that time. They allowed us to go and sample exactly as I've just described, taking some of the contaminants, using a nutrient solution and seeing what grows and seeing how the oil is being used by these collection of microbes forming these balls. And from there, we isolated organisms. And my PhD student, who is actually a Singaporean, was playing with how to develop a technology around treating the groundwater, which was contaminated with phenol from the treatment of crude oil. And so he used this wastewater, which was the phenol-contaminated water. He used ceramic beads because he saw the way the microbes were growing and thought they would grow best surrounding a matrix and just bubbling air through. So in the laboratory, a really simple system, but he completely developed de novo. And here you can see a control treatment where the level of phenol, measured as chemical oxygen demand here, remains fairly constant over 4 days. But in the treatment where we have these microbes, we saw a 3-fold reduction in just 4 days of the chemical oxygen demand. What does that equate to? That equates for somewhere around $2 or $3 million a year in fines that they don't have to pay, the Singaporean regulatory agencies, because their fines are based on how much COD you have in your water supply that's being treated. So instant saving, and that is significant. And it made a big impact on the Singaporean government and the inhabitants of this island, as we'll see. Moved on. How do we do this on large scale? How do we commercialize the technology? That's what we're really interested about, making a difference, translating what we find into the field. Lo and behold, he used an ISO tank, which was sitting around on the site. He's grew his bacteria from a flask into this ISO tank. He pumped his bacteria into the groundwater, and he then took more groundwater back into the tank and inoculated that. So the organisms were growing in here, being released back into the groundwater, where they continued to be effective. And lo and behold, this treated 200,000 litres of water contaminated. And you can see here what happened in the field, in both measuring chemical oxygen demand, which is what they were charged, the company being charged against, but also the phenol itself. From somewhere around 1,800 milligrams per litre to barely detectable in just 32 days. And it was continually being recharged. So there was contaminants going there all the time. But these microbes were able to exist in the environment and keep that population going down. And this is Greg Poi, receiving the award from the iChemical Society in Singapore for the best sustainable remediation project in 2017. And it was runner-up on the international front. So a really great idea, This is still going. This company are now using this system day in, day out to continue these numbers. Bioremediation. All we do is provide an inoculum of microbes that go into that tank every month just to refresh. Very, very impressive technology. And it's all based around deriving what's around, making use and designing and engineering new solutions specific for this particular environment. Very often with bioremediation, once you show that it's effective, the company come back. Most companies are skeptical because it's not something they've become familiar with. They're engineers. They want to see things being moved and transported. But once the company here got involved, they said, we've got a very difficult soil problem. You wouldn't be able to treat that too, would you? So here we are. They said, we've got no room. You can have a small 50 square meter pad. It's all we can give you. It's all that's there. So again, Greg, myself designed the pad. We put some soil in there, which was contaminated. We added our inoculant because they were so scared of having any pumps, any electrical systems. The company manually poured the inoculant and the nutrient over the soil. So lo and behold, we had to put a cover on it because of the rain. We needed to keep the rain. Obviously in Singapore, it's quite intense at times. And there we are, treating 50 cubic meters at a time of the same island. And instead of shipping it off to another island to be dumped, the idea was to reuse this soil on the island, to build up the island. Amazing. Again, through the same approach, bioremediation. Here's the control. So this is the soil. Again, total petroleum hydrocarbons, 35,000 milligrams per kilo. Very high contamination. And if you leave the soil, it naturally attenuates. But if you add the organisms, which are now patented, look how effective that is in just 21 days. We're ready for the next batch. And it doesn't matter how contaminated the environment is. This is, 50 or 60% oil. And we're seeing starting concentrations, finishing concentrations after 9 weeks. The red bar here shows you how effective this technology is. Again, still working. I'm very proud of Greg. He got the runners-up prize, or we got the runner-up prize for that particular biotechnology project in the same awards. And it probably won't surprise you to know that Greg has his own company in Singapore. He runs a bioremediation specialist company and is very, very successful. So a translation story from Dr. Poir. Moving on, it's oil and hydrocarbons are something which microbes, as I said, have been around a long time. What about more difficult, more complex compounds that don't exist naturally, like chlorinated compounds, perchloroethene, trichloroethene, which were used for a long, long time in dry cleaning, used as degreasing agents for almost 70 or 80 years. We now know that these are extremely carcinogenic and mutagenic compounds. And they exist in our groundwater now. So they're heavier than water, so they sit at the bottom of the groundwater. And they're very difficult to treat, and even at low concentrations, they're regarded as highly hazardous and highly carcinogenic. As you can see here, even though this is historical, we don't use these compounds anymore. Here's in the heart of Adelaide, just 10 years ago, a warning. The bore water was contaminated in Plimpton with this contaminant. Still very much difficult. If it contaminates the groundwater, that destroys its function as a drinking water source. And it's below the ground. And it may be even below buildings. So how do you remediate? How do you get a digger? You don't. How can you thermally desorb? You can't. Bioremediation is one of the only effective technologies besides pumping the water out, treating it and pumping it back. So you can fracture to recover the groundwater, so somehow destroy the flow path of the groundwater and pump it out. But then you have to replace that water with something, otherwise a hole in the ground will form. You can try using something called permeable reactive barriers, which is something you place in the stream flow of the contaminated groundwater, and the contaminant will bind preferentially to those reactive barriers. But you have to put them in there, and they have to be in the flow of the entire groundwater flow to be effective. So you have to have a lot of understanding of hydrogeology. Or you can use bioremediation to try and solve this issue. And it's something that has been very, very effective. So these are chlorinated hydrocarbons. So the hydrogen has been replaced by chlorine, which is not a naturally occurring compound, or very rarely. One of our recent projects is actually looking again historical contamination in Western Australia, where they had a lot of plants that generated electricity using crude oil as a source. And obviously, historically, that included lead. So heavy metals are difficult. They don't break down, of course. You can transform them, but you can't actually break them down. So phytoremediation, using plants, is a really effective way of taking heavy metals out of the soil. And it's been very effective. Whereas using bacteria, they can assimilate the heavy metals, but they tend to remain in the soil. So plants and phytoremediation is the real bioremediation approach, and it has been used many, many times and very successfully. About 10 years ago, we found, and not myself, but researchers identified this tiny organism, never been seen before, Dehalococcoides. It's only 1 micron in length and 0.1 micron in width. And it has this kind of a stalk. It's only found in groundwater, but remarkably, it was able to break down very effectively these chlorine groups by sequentially taking off a chlorine group. So you have 4 chlorine groups, you have 3, 2, 1. This is vinyl chloride. And then finally, you produce ethene. So it's a reductive dechlorination. You're reducing the compound. And ethene can be assimilated, and you can remove this compound from the environment once and for all. Tremendous technology, tremendous organism, and is the basis of an amazing technology. In fact, you can buy these strains now. They're commercially available for you to buy off the shelf and tip into groundwater. Now, we're not advocates of that because they may not be indigenous to Australia, to our groundwaters. We want to use naturally occurring organisms. So we shied away from using commercially available to deal with our issues. You can add an organism, a non-indigenous organism, to the environment. In much of my research, I found that they're very ineffective because you're putting them from another environment. They're grown in a fermenter, and you're placing them to compete with organisms which have been in that environment for a long, long time. And it's a big ask to get an organism to suddenly turn up in a new environment and starting to compete with the rest. Whereas microbial communities, these thousands of species, have been working together for, again, countless eons. And they've developed very effective tools and technologies. They're communicating to each other. They're building biofilms of different organisms with different capabilities. So actually, I always look for the solution where you find a contaminant. You just have to learn or understand what's stopping them from degrading a contaminant, assessing whether they could do it, and if so, how you do it. So very much focused on microbial communities, not single species, and how they interact. And it's a wonderful time using these approaches we have now to start understanding how these networks of microorganisms are so effective. And just like Adelaide, Melbourne also has issues with chloroethene. Again, the site of an old industry that were using dry cleaning products, an old tank that had these compounds in, tank leaks, ruptures, and you could see that there's very steep decline on this particular topography into the ocean. So large quantities of this contaminants, which is a carcinogen, a mutagen, were found and very difficult to remove any other way due to the presence of buildings and infrastructure. These are bore wells, so we can follow where the path of the flow is, and we can monitor the concentrations of the contaminant. And this is Taylor introducing that biostimulation, just using simple materials like olive oil, lactate, to help a carbon source that helps drive these microorganisms. Over 7 months, this is a concentration of our starting material, which was perchloroethene. And you can see what happens. The arrows here show you when we added our biostimulant, just tipping in nutrients to drive the microbial community. And you can see as soon as we started, the contaminant was being removed. But remember, it's a sequential dechlorination. So you don't just see the end product. you find an intermediate. So one chlorine is removed. Look what happens. Dichloroethene starts to raise up in high concentrations. But trichloroethene is being removed. Then the microbes carry on. That sequential dechlorination. They dechlorinate the dichloroethene to vinyl chloride. Just one chloride group left. That's a very dangerous moment because vinyl chloride is about 1,000 times more dangerous than the starting material. So you really have to make sure that you understand the bioremediation. Otherwise, you're exasperating the situation. But here is our product, ethene. This innocuous product has no environmental implications as our final product. The vinyl chloride, dichloroethene, trichloroethene, completely removed. Without invasive, without digging, we've returned that groundwater back to a safe and effective water source. So again, bioremediation in action, even when you can't see it. That example of chloroethane degradation is unusual in that we do understand the process very clearly about the reductive dechlorination. But with for example, polyaromatic hydrocarbons, a component of oil, there's thousands of different products in there. It's not one single carbon-containing compound. And when you start to break them down, it's impossible to follow all of the compounds that are broken down. And in those scenarios, we might be producing more toxic compounds. So building into your bioremediation assessment of toxicity, ecotoxicity, because you may have transformed your product into something more dangerous. And it's very hard to find a compound that you don't know what you're looking for. But if you assess the toxicity as that bioremediation continues, it's a very safe technology to make sure that what you're producing is a safe, effective treatment, not just reducing the original parent compound and producing a whole array of others. Well, how did it work? What was happening there? Well, I talked about Dehalococcoides as being something that was found 10 years ago, as being very effective in removing them. We didn't have to buy them. They were there already, naturally occurring in that groundwater, along with another organism called Geobacter. And how we did that? By adding that nutrient, we changed the concentration. So these are the control samples, how many Geobacter were here. This is the number of cells. By the end of our treatment, look how many cells there were. From 10 to the 2 to 10 to the 6. Huge increase in the number of the organisms that can break down the contaminant. And that's true of both Geobacter here and our good commercial friend Dehalococcoides. It was naturally present in the groundwater, and we just helped them to generate large numbers and to be effective. Will they persist in the environment? Have we changed the microbial ecology of that groundwater? No. As soon as the contaminant is being used up, it loses its selective pressure and it starts to reduce back to the control levels. But if there was another contaminant level, another source, then we'd see the same thing. So it's future-proofing as well, the microbiology of the groundwater. So it is resilient to future contamination. There's been many, many important breakthroughs in environmental microbiology over the last 50 years. But the use of technology involving DNA has been absolutely profound in helping us understand the microbial community and what they do. And instead of trying to isolate organisms, we just extract the DNA from the environment. And in theory, we've got a handle on every organism that was in that environment. And we can start to understand much more what we've done. And so this is DNA that extracted from those groundwater samples. This is the control. And effectively, each of these bands is a class of bacteria. And these are the different names. And you'll see this is the sort of pattern that we see in the control, non-contaminated water, and in the contaminated groundwater that we start before any treatment. So those two are quite similar. And this is where our concentration of trichloroethene is high. Skip 7 months and see what we've done. How can we explain the effectiveness? Well, the big thing in our treatment is this group of organisms, the epsilon proteobacteria. They're the organisms that we looked at. Look how they've increased in the relative abundance in that population to be able to remove that contaminant. The control, uncontaminated, still has a very similar microbial community to the starting material, But that's what we've done. And we would expect these numbers to decline as the contaminant is removed. Tremendous. So this technology, this DNA approach is really making us understand and being able to manage the process, make big improvements in bioremediation. Coming towards the end now, what is the future challenge? We are heading towards a future that doesn't have oil, that doesn't use some of these pollutants. Is bioremediation going to fall by the wayside as a technology only for legacy products? I believe the answer is no, because unfortunately we are still polluting our environment day in, day out with a whole range of new products. From the perfluorooctane sulfonate, the PFOS and perfluorooctanic acid, the material that's used in Teflon, the material that was used in firefighting foams, to waterproof our clothing, to waterproof carpets, stain resistant. It was been around for a long, long time. And this is the compound which is in our environment, it's on our homes, it's in our blood, it's in the blood of newborns. We need to find a solution as to how we remove them. But this is perfluoro. They're fluorinated compounds. They're completely unnatural. No microbe has ever seen these organisms before. And that carbon-fluorine bond is so strong. It's one of the strongest bonds in chemistry. Very hard to break down. Microplastics. We're finding them in the environment. We're finding them in our soils. We're finding them in our wastewater. We're putting that back onto our environment. We need to find a solution that destroys the microplastics. Can microorganisms be the answer? They can certainly, evidence is now gathering that we have enzymes capable of bacterial enzymes capable of breaking microplastics. Polybrominated compounds, all these compounds are man-made and they're resilient because they are man-made and are not persistent in the environment for billions of years. So flame retardants, PDBs, military explosive, moving on from traditional dynamite type explosives, RDX, very common contaminant obviously on Department of Defense sites. But what about us? We use every day personal care products. We use them in our own homes. We're putting that into wastewater treatment. Well, water is recycled. It's reused in the environment. So moisturizers, perfumes, polishes, shampoos, all of these toothpastes are all turning up in our environment. And we need to find a solution. Many of these things, we don't understand what impact they're having on the environment. But if anything we can learn from the past, it will be having some environmental impact, changing. If we want to improve our ability of our soils to sequester carbon dioxide, we need to have these ecosystems functioning at their optimum. We don't need to be challenging them with these compounds. Nanomaterials, we use them in hospitals for treatments. We use them silver in our clothes to prevent odor. Wash the clothes, then many of these nanomaterials enter the environment. They're very, very effective materials because they're nano and they interact with a whole range of organisms and processes. So the future is, where does bioremediation, how can we deal with these technologies, these new products, these new challenges for bioremediation? And here's where we're going to have to move back into the world of DNA and understanding communities and what they do and start using synthetic biology, creating new biological parts, new devices, new systems targeted at utilizing the basis of a natural occurring enzyme, in this case, something called P450, but changing them. In this case, this was putting iridium atom instead of an iron atom. This organism, this enzyme, took on completely new activities. So it's present in E. coli. This was Berkeley. And you can see that they haven't disclosed what it's capable of doing. But we can design new systems based on natural enzymes to try and target some of these new products. So that's the future. There's a lot of synthetic biology that's going to have to occur to improve the ability of plastic degradation, biodegradation. So we can remove these plastics from our soils, our composts, our biosolids, and our waters. So I believe the future of biotechnology and bioremediation in particular is one that's going to be diverse. It's going to be based on a lot of new innovations and technologies. But we've learned so much from bioremediation in the past 20 or 30 years that I feel confident that we can tackle these new emerging pollutants effectively using bioremediation. Very much at the moment, it's left with the water industries or the landfill companies or the composters who are dealing with trying to remove these contaminants from products. And of course, they're the end users and they're being penalized, which is affecting, the application of compost, for example. Fantastic fertilizer. But, because there may be contaminants in there, people are starting to think twice about using it. Same for biosolids. 70% of all biosolids in Australia from wastewater treatment goes on the land. It's a fantastic fertilizer. It's completing a circular economy. But because of the contaminants that are coming from our industry and households, there's a risk now. There's a risk that they will be reduced in terms of their application because of the threat of the contaminants. And that really the emphasis has to shift back to the manufacturers. Finally, I'd just like to acknowledge the funding bodies that made a lot of this work and research possible over a long time. The Australian Research Council, who've been a fantastic supporter. Industry, Victorian industry are really engaged in finding solutions. They will support and they have supported new initiatives and ideas. State government, again, a very important source of trialing new technologies. RMIT University, my own university, have been incredibly supportive and working at translating research, pushing us to take our research from the laboratory into the environment, to translate it. Those students, 80 plus students who've worked with me for their PhDs, 30 or so postdocs who've been with me, all those collaborators from around the world have been important. And of course, all the family and friends who've supported through all of this research to make it a really effective group of researchers that have developed some very interesting and are developing new technologies all around the world based on these bioremediation principles they learned here. So thank you very much. I really like people to think about, what they're producing in their homes. Start with the homes. Start with the products that you're using. Everything we use and we throw away or we flush away, we have to start thinking, well, what happens to that? It goes somewhere. It goes for treatment. It's a really important process. But at the moment, there's a lot of those products which will go through the treatment unaffected and will end up in the environment, end up in the biota, of Australia, end up in some of the things that we're going to then use and consume, plants, animals. We have to take responsibility, I think. Every individual needs to look and try to minimize the footprint in terms of what they're producing, make things sustainable, use things that are degradable. And I think, pass that message on. If there's enough people saying that message, then industry will start to invest more in new technologies, less invasive technologies perhaps, less of a threat to the environment. Legislation will be able to be tightened. And that will be an important step in our sustainability of these unique Australia flora and fauna.